Hello everyone, this is Dr. Babu. Currently I was working as an assistant professor in the Department of Electrical and Electronics Engineering at the University Surampalem. Today in our Electrical Network Analysis 2 subject, we are going to discuss about three-phase circuits. In that, we are concentrating on module 3 of part 2. Here in the previous class, we have discussed about analysis of a three-phase unbalanced circuits. In this three-phase unbalanced circuits, we have discussed about delta connections and three-phase 4-wire system also we have discussed. Now the leftover part is three-phase 3-wire system. So in three-phase 3-wire system, the loop method is one of the technique, star delta transformation is one of the technique, and Milliman's theorem are one of the technique. So in these three methods are used to solve then three-phase unbalanced circuits, and we will be going one by one. As star delta transformation is very easy, we will be going to start our session with star delta session, followed by loop method and Milliman's theorem. Star delta transformation. In the screen you can observe that the left side is star connection and the right side is delta connection. So in the left side you can observe that it is a star connection R by B phase, and in that ZR is the impedance across R phase, and ZB is the impedance across B phase, and ZY is the impedance across Y phase. Whereas this IR, IY and IB are the respective line currents across R phase, Y phase and B phase, and also VRY, VRB and VYB are the line voltages. Now we are converting this star connection towards delta connection. Now let us go to the delta connection in a conventional way, where delta connection in the sense it will be in the triangle form. You can observe it here, and it contains three phases: first phase, R phase, Y phase and B phase, and here IR, IY, IB are the line currents as well as phase currents, because in delta connection line currents is equal to phase currents. And after that here ZRB, that means this is the impedance across R and B phase, and this one ZYB, this is also impedance across B and Y phase, and similar manner RY, and the current flowing through ZRB is IRB. In a similar manner, the current flowing through ZRY and ZYB is IYB and IRY. So this IRB is here, IYB is here, and IYB, IRY is here. These three are the phase currents. Okay, now we are going to convert this star connection to delta connection. The reason is, suppose if you are moving on from transmission side to distribution side, or distribution side to transmission side, in the case of transformers, there will be star delta connection or delta star connections. So in order to convert delta to star or delta star to delta, you should be familiar about these kinds of connections. So now we will start with the connection and conversion part. Okay, I think it is this is visible over here. See here. Now I am converting this star to delta. That means here it will be ZRY. Okay, that means this ZRY is connected across this position. This is nothing but ZRY. Now in order to calculate this ZRY, you can simply remember by using a formula. This ZRY you can write it as impedance of ZR ZB sigma divided by the opposite side impedance is ZB. Okay, you can observe it, see here. That means in order to find out this ZRY, it will be ZR into ZB plus ZR into ZY plus ZB into Z. Now I am rewriting it a proper way. ZRY is equal to ZR into ZB plus ZR into ZY plus ZB into ZY divided by opposite side impedance is ZB. Okay, I think this is clear. So here ZRY you can observe it, see here. We got the ZRY connection, ZRY value. Now I am going for ZYB, that means this part. In a similar manner, ZYB is equal to in topmost is same, sigma ZR into ZB divided by, for ZYB, what is the opposite side impedance? It is ZR. Therefore, ZYB is given by sigma ZR into ZB by ZR. So, this is the another impedance part. and the next impedance is ZRB. That means this is connected across R and B phase. This is ZRB. Now in order to calculate this ZRB is equal to similar manner sigma of ZR into ZB divided by, for this ZRB the opposite side impedance is ZY over here. Therefore ZRB is given by ZR into ZY plus ZY into ZB plus ZB into ZR divided by ZY. That means we have calculated the total impedances in delta connections. Okay, that means from star we have calculated the values of impedances in delta, and after that we need to calculate the impedances of you need to calculate the values of line currents and phase currents and line voltages and phase voltages. Now we will be going to look one by one. Okay, now first step is calculations of phase currents. Okay, so here in this ZRB the current flowing through it is IRB, and this ZRY the current flowing through it is IRY, and ZYB current flowing through this is IYB. Okay, now here see, for IRY is equal to, we have taken the reference of VRY as reference. Therefore VRY at an angle 0 divided by the opposite, the admittance of it is Z times of RY. Okay, in a similar manner IYB. So for IYB it will be VYB at an angle of minus 120 degrees divided by ZYB. In a similar manner you need to calculate the values of IRB. Therefore IRB is equal to VRB at an angle of minus 240 it will be divided by ZBR. Okay, so now we have calculated the values of phase currents in delta connections. After calculation of phase currents, we are supposed to move on to the calculation part of line currents. Okay, as discussed earlier in the previous classes, in order to calculate the line currents, you need to write the KCL equations at the nodes A, B, C. So if we write the KCL equation at node A, KCL at node A, if you observe, this means IRB is entering, okay, plus another current entering is IR, that is equal to leaving currents. Leaving current is IYB, sorry, IRY. Okay, therefore the line current IR is equal to IRY minus I times of RB. Okay, this you got it. In a similar manner, if you calculate the values at current values at point B and C respectively, you will be getting the line currents of IY as IYB minus IRY and IB as IBR minus IYB. Okay, now next I am moving on to the calculation of the voltage across the impedances, that too in star connection. So here if you observe, this means this part, here we will be getting impedance N. Okay, so therefore the voltage value across ZR is, we all know that voltage is equal to current into impedance. Therefore VRN is equal to current is IRN and the impedance value is ZR. Okay, in a similar manner the voltage across ZY is, the current flowing through it is IY, okay, and the impedance across it is ZY. In a similar fashion, the voltage across the phase B is, so the impedance B is, ZB is the impedance and current flowing through it is IB. Okay, now we have calculated the values of line currents and phase currents in star delta connection, and also the line voltages and phase voltages in star connection. Now let us look into a numerical, so that we will be getting some idea of how to solve with the help of this star delta conversion method. Okay. See here, if 3 phase 440 volt, that means supply voltage is the 440 volts 3H, and they have mentioned is unbalanced and also 3-wire star connected load. That means star connected load. Okay, let this be the star connected load, and here somewhere it will be 440 volt. The supply is 440 volts, R phase, Y phase, B phase. Okay, supply is 440 volts, and ZRN, this is 10 ohms, and ZYN, this is 15 ohms, and ZBN, it is 20 ohms. Okay, now they asked us to find out the line currents by star to delta. That means first we are supposed to convert this star network into delta connected network. Now I am doing it the same. See here. Okay, now I have connected this impedance across Z, B and R. That means this value will be ZRB. If I connect the impedance across YB means ZYB. Next one, left over terminals are across R and Y. So now I am connecting across this one, R and Y. That means this value is ZRY. Okay, what is the first step? In the first step, we need to calculate the values of ZRY, ZYB and ZBR. Now let us do the thing. Now I am calculating the value of ZRY, where ZRY is equal to, as I told you that the ZRY opposite value is 20 ohms. So it will be in the denominator part. Okay, it will be in the denominator part, and the remaining all we should multiply. 10 into 15 plus 20 into 10, 10 into 15, 20 into 10 plus, and 20 into 15. So if we calculate this part means 10 into 50 means 150, 20 into 10 means 200, and 20 into 10 means 350 divided by 20. The total value will be 350 plus 150 will be 500, 500 plus 2 will be 700, 700 divided by 20, 0 gets cancelled. The value of ZRY is 35 ohms. Okay. In a similar manner, I need to calculate the values of ZYB and ZRB. Now I am going to calculate the value of ZYB at first instant. ZYB. Therefore, for ZYB, the numerator is same. So the numerator value is around 700, and for ZYB the opposite value is 10 ohms. Okay, this is ZYB. Its opposite value is 10 ohms. I am writing it here. 0 gets cancelled. The value of ZYB is 70 ohms. Next, I am going to calculate the value of ZRB. So ZRB, the opposite value of ZRB is 15. So denominator part I have written the 15, and the numerator part it is all same for all the things. So 70. Okay, 5 3s 15, 5 1s and 5 4s 20. It will be around 14 divided by 3. Okay. Now I got the values of all ZRY, ZYB and Z. That means I got the values of the impedances in delta connection. Now I am writing those values over here. See, for our purpose. ZRY is 35 ohm, ZYB is 70 ohm, and ZRB is 14 by 3 ohms. Now I am erasing this part so that in order to go further. Okay, now they asked us to find out the values of line currents. Okay, now I am redrawing the circuit. ZRB, ZYB and ZRY. Okay, this ZRY is 35 ohm, ZYB is 70 ohm, and ZRB is 14 by 3 ohm. Okay. R phase, Y phase and B phase. Now the thing is, I need to calculate the values of line currents. Line currents means this one is line current, IR, and this is IY, and this is IB. So I need to calculate the values of IR, IY and IB. In that, this current flowing through it is IRB, and the current flowing through it is IRY, and the current flowing through it is IYB. Okay. Now to calculate the values of IR, IY, IB, I need to calculate the values of IRB, IYB, IRY. Okay. Now I am erasing this part. Therefore, IRB is equal to, no, first we need to take RY as reference, right? So, IRY is equal to VRY at an angle of 0 divided by ZRY. For VRY at an angle of 0 in the sense 400 volts at an angle divided by 35 ohm. Calculate it and write down the value. And in a similar fashion, IRB is equal to VRY at an angle of minus 120 degrees divided by ZRB. Okay, therefore it is 400 at an angle of minus 120 degrees divided by the value of ZRB is how much? 14 by 3 ohms. Write it and calculate it and write down the value. Next one is IYB. IYB in the sense VRY at an angle of minus 240 degrees divided by ZRY. Therefore, VRY means 400 at an angle of minus 240 divided by ZRY. The value of ZRY is 35 ohms. Calculate it and note down the values. So, after the calculation part, we will be getting the values of IRY, IRB and IYB. Okay. Now, because the same procedure we have done it in delta connection method also, currents, so that I am giving you an idea how to solve the problem, but I am not solving the numerical completely. Okay. You need to calculate the values. That means I got the values of IRY, IYB and IBR. Now I need to calculate the values of IR, IY and IB. Okay, I am making this as node 1, this one as node 2 and this point as node 3. At node 1, I am applying KCL. KCL is nothing but sum of entering currents is equal to sum of leaving currents. Therefore, here the entering currents are IRB, okay, IR, leaving current is IRY is equal to IRY. Therefore, IR line current is equal to IRY minus IRB. And at node 2, if I apply KCL means the entering currents are IY is entering and the current entering is IRY. You can observe it here. And the leaving current is IYB. Therefore, the underlying current IY is equal to IYB minus IRY. at node 3 if I apply KCL means, here the sum of entering currents are IB is one current entering and the another current is IYB. The leaving current is IRB. You can observe it over here. Therefore, IB is equal to IRB minus IYB. Okay. The values you got as IR, IY and IB are line currents. So, this is the procedure for solve an unbalanced star connected load, that means star to delta connected load. Now, I am moving on to the next method, that is loop or mesh analysis. This method is also very similar and very easy. Okay. In loop analysis method, you are simply applying KVLs. Okay, see here. See this circuit diagram, the diagram over here. This is R phase, Y phase and B phase. ZR, ZY, ZB are the impedance across its phases R, Y and B, and IR is the line current flowing through the R phase. In a similar manner, IY and IB are the line currents flowing through the phases Y and B. In star connection, the line current is equal to phase current, right? So currents is same, but the voltage values will be varying. So in order to calculate this, solve these numericals, we need to apply the KCL technique. Now I am assuming a loop here, first loop and second loop. Okay, because in most of the textbooks they have taken in this model, or else you can apply a loop over here also and you can get the value. That means either two loops is enough to solve the solution. So for that purpose, I have taken only these two loops. Okay, now see this one, VRY. Okay, across VRY, if I am applying KVL in the sense, yes, it is clearly written over here, VRY. VRY at an angle of 30 degrees in the sense, if I take VR as a reference, it will be at an angle of 0. If I take VR means it is an angle 0. Now I am going for VRY, it is at an angle of 30 degrees. So VRY is equal to, see here, this one is I1 current, right? I1 into ZR plus, see here, in this node, I1 is leaving, I1 is entering, and I2 is leaving. Therefore, it will be I1 minus I2 into ZY. Okay, that means one current is entering, another current is leaving the node. So that's entering in the sense positive and leaving means negative. This is for VRY. If I write it for V by B, this will be at an angle of minus 90. Okay, this one 4 is 4. First one is this one. It is I2 minus I1. I2 minus I1 into ZY plus I2 into ZB. Okay, so we have wrote these two equations 1 and 2, and now if we solve the values of 1 and 2 equations, we will be getting the values of line currents I1 and I2. Now if you need I1, I2, we will be getting the values of I1 and I2, but we need to calculate the values of IR, IY and IB. So for that, if you observe this loop means, this IR is equal to I1 over here, okay? So this one is this, and if you observe this 2 means, this I2 is equal to minus of IB, okay, because both are in opposite direction. Here both are in same direction, that's why it is positive. Here both are in opposite direction, so that's why it is negative. And the leftover current is IY. So in IY, it will be I1 minus I2. Okay, this is the procedure in order to calculate the values of line current. In order to calculate the values of phase voltages, VRN, that means here tilde here, VRN is equal to the current flowing through this phase is IR into ZR. Okay, and if I need to calculate the voltage across VBN means the current flowing through it is IB, okay, and the impedance value is ZB, and in a similar fashion for this thing. And regarding this method, the numerical, we will discuss it in the next session. Okay, thank you.